All right, anyways, derivative. So you can read this first part. This is read f prime at a, right, f prime at a. So the derivative can be interpreted as the blank of a tangent. So the slope of a tangent. Slope. The tangent line to the curve y equals f of x at the point a, comma, f of a has a slope of f prime at a. So if we can figure out what this f prime is, then we have an expression for the slope at the point A. The blank rate of blank, which is then given in the next two words, right? So it's the instantaneous rate of change, right? So it's the slope or it's the instantaneous rate of change. Instantaneous rate of change. The instantaneous rate of change of y with respect to x when x is equal to a is equal to f prime of a again, right? So it's the slope of the tangent line or the instantaneous rate of change. In particular, if s of t is the, what did we call s of t? Starts with a p. Ends with an ischen. Position. Position function of an object, right? It's just saying where it is, right? What is its displacement? So in particular, if s of t is the position function of an object at time t, then the blank of the object at time t equals a is given by s prime of a. So what was that? We have a position function. From that, we're going to get the velocity. Yeah. The velociraptor of the, yes, how to make calculus cool. Then the velocity of the object at time t equals a is given by s prime of a. In other words, v of a is equal to s prime of a. If you want the velocity, then you need the derivative of the position function. Example 1. For f of x equals 2x squared minus 4x minus 1, determine f prime of 4. Okay, so we're going to do this by using the formula, right? And another way to say that is we're going to use first principles, right? So first principle is just, and that's all we know to do right now, right? We're going to learn ways because, you know, if you're going to do a lot of this stuff, there's got to be an easier way than what we're doing now, and there is, but for now, this is what we got. Okay, so I want f prime of 4. So f prime of 4 is going to be equal to the limit as h approaches 0 of f of 4 plus h minus f of 4 over h. And so now it's just algebra, right? We're gonna, so that's equal to the limit as h approaches 0. So f of 4 plus h would be 2 times 4 plus h quantity squared minus 4 times 4 plus h minus 1. Okay, now that corresponds to f of 4 plus h. So I'm just going to, bracket it to say, set that aside. Minus f of 4. Okay, so again, we'll throw this one in brackets, especially because we have the minus sign here. So, once we've simplified, we're going to want to remember to subtract. So 2 times 4 squared minus 4 times 4 minus 1. Okay, so this is f of 4 plus h minus f of 4 all over h. Which is equal to, okay, keep going, the limit as h approaches 0. And now we need to expand this. So what do we get? How much detail do we want to show? Well, 4 plus h squared is what? 16, and plus 8h plus h squared, then that's all multiplied by 2, right? So it's going to be 16, so we'll make that 32. Plus 8h, okay, but we've got to multiply by 2, so let's go plus 16h. Plus h squared, multiplied by 2, so plus 2h squared. Minus 16, minus 4h, minus 1. All right, so that's the expansion of this. I don't even know if I need that bracket anymore, because we could just work this out, right? What is that? That's 16, that's 32, minus 16 is 16, minus 1 is like 15, right? So it's going to be minus 15. Or do you want to, well, let's write it out. So let's go minus 32 plus 16 plus 2. All over h. Okay, so is that right? Minus, we get 16, 32, minus 32, plus 16, plus 2. Okay. No, wait. Sorry, there's no 2 there. Hang on, that's a 1. Plus 1. Oh, yeah. Yeah, I'm not multiplying this through by 2 like I did this. So, okay, 32 minus 16. All right. Okay, what can we do? Well, we got a 32, we got a minus 32, right? So here, let's do this in red by moving the black pen. So 32 minus 32 minus 16 plus 16 minus 1 plus 1. Okay, what's left? So we've got, okay, so can we just scooch up here? Let's go up here. So what do we got? 2h squared plus, okay, what? 16h minus, so 2h squared plus 12h? Yes. Yeah? Okay. So we've got the limit as h approaches 0 of 2h squared plus 12h over h. Yep. Hang on, pause. You can kind of finish it up. Where are we? The limit as h approaches 0 of, and there's equal signs here, I guess, right? Of what? So we got 2h and then h plus 6 over h. So that's 2 times 0 plus 6, which is 12. Right? Because at this point now we can drop the limit, right? Because now we can put in the h value of 0. So there's h of 0 and 2 to the 12, right? Right, 2 interpretations of f prime at 4 equals 12. Well, this does one thing. We know we got it right, because, hey, look, f prime of 4. That's, well, ultimately that's what it was, right? Here's the f prime at 4, and then here's the equals 12. They're just kind of separated by a smidgen of algebra. Luckily, you won't have to do them this way all the time, right? But it's good to see it, and I'm not going to say you'll never have to do it again, and we'll be doing it the rest of today. Then we'll learn stuff to get away from that, but on the test of derivatives, which is March 17th, so that's still a ways away, you may have to do one from first principles, right, as well as on any cum or final or something. All right, so 2 interpretations. Number 1. All right, what is this f prime of 4?
Velociraptor.
Velociraptor. Only if it were a positioniraptor to begin with, but it's not. So f prime at a is the slope of the tangent line, right? So f prime of 4 is the slope of the tangent line, right? So the slope of the tangent to y equals f of x. The slope of the tangent to y equals f of x at x is equal to 4, okay, so or when x equals 4, I don't know, what do you like, when or at? I'm going to say when. When x equals 4 is 12. Okay, so the slope of the tangent to y equals, I never graphed this or anything, right? I mean, we could do that in Desmos, and then we could, you know, throw down the 12 line slope, and we would see that it would be the tangent line. And what else is it? It's slope, but it's also the instantaneous rate of change, right? So we could say the instantaneous rate of change of f of x. The instantaneous, which cannot be written instantaneously. Rate of change of f of x with respect to x, of f of x, change, rate of change of f of x with respect to x is at x equals 4 is 12. We'll give equal time to at. We got a when, we got an at. Well, what that's saying is when x is 4, the y values are changing at 12 times the rate the x values are changing, right? That's their instantaneous rate of change. So just another way that we can phrase this is the y values. So the y values are changing 12 times as fast as the x values. The y values are changing 12 times as fast, 12 times as fast as the x values at x equals 4. So the instantaneous rate of change is 12, right? So the y values are changing at 12 times the rate the x values are changing at that point when x is equal to 4. Determine f prime of x for the general point f of x, and use this formula to determine f prime at 4 and f prime at 9. So the thing is, if we're just doing f prime, like we did an awful lot of work to find f prime of 4, right? Now if we had to do that work again to do f prime of 9, it would be a lot of work. And then if we had to do f prime of 7, so let's come up with a more general formula for it, where we can just say f prime of x is equal to, and have an expression in terms of x, and then we can plug in a 4, and then we can plug in a 9, and we can get that rate. So basically we're just going to kind of do the same thing we did above, but we're going to do it in general. Okay, so f prime of x instead of f prime of 4. F prime of x is the limit as h approaches 0 of f at x plus h, right? Because we're dealing with the x now, over h is equal to the limit as h approaches 0. Okay, so what's the definition of the function? So it's going to be 2 times x plus h squared minus 4 times x plus h minus 1. Okay, so that's f of x plus h, right? That's f of x plus h minus f of x. So minus 2x squared minus 4x minus 1 all over h. Okay, and now it's just do a little bit of algebra. Expand and collect. left of the page a little because... Okay, so we're going to remove brackets. Why not remove brackets? So what do we got? We got x squared plus 2xh, so 2x squared plus 4 xh. Let's go with xh. Plus 4xh plus 2h squared minus 4x minus 4h minus 1 minus 2x squared plus 4x plus 1 over h. Okay, and then just as above where there were numbers like 32 and a minus 32, we have a 2x squared and a minus 2x squared. We got a minus 4x and a plus 4x. We got a minus 1 and a plus 1. Okay, so is that it for canceling stuff? Okay, so the limit as h approaches 0. So what's left? We got 4xh plus 2h squared minus 4h over h. So we can factor out a 2h out of the top. So over here, limit as h approaches 0 of 2h. And what do we get? 2x plus h minus 2. Okay, so is that right? 4xh, 2h squared minus 4h. Yep. Over h. Oh, don't forget an equal sign here. Okay, so those guys cross off. So that equals 2. We've got 2x plus 0 minus 2, right? Because now it's okay to put in the h as 0. Okay, so 2, h is gone. 2x plus 0 minus 2, which will be 4x minus 4. And what was that? That was f prime of x. So a general formula for f prime of x is 4x minus 4. So then f prime of 4 is 4 times 4 minus 4, which is 12. Thankfully, right? I mean, you'd hate to all of a sudden have it change its value on us. And f prime of 9 is 4 times 9 minus 4, which is, what, 32? Right. So we can say the instantaneous rate of change of y with respect to x at x equals 9 is 32, right? It's changing 32 times as fast. Okay. So the derivative can be seen as a function of x. Given a function f, the derivative of f is the function f prime, defined by f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. And a function is said to be differentiable at x equals a if f prime at a exists, and f of x, the original function, is continuous at a. Okay, so I mean, if there's a hole there, you can't find a derivative at that point, right? A function is said to be differentiable on an interval if it is differentiable at every number on that interval, right? So you think sometimes, you know, we have a function that describes something, and really we only care about like from 0 up or something, right? Maybe it's time, maybe it's a motion graph and time is 0. We only care about the interval from, say, 0 seconds to 6 seconds or whatever that describes this parabolic path, right? And then if it's differentiable on that interval, then it's fine, right? And even if it's not defined somewhere outside of that interval, we're okay with it if we're just working in the interval. Okay, so pretty kind of good with this page. Example 2. If g of x is the square root of 2x minus 1. Okay, so we are going to determine g prime of x. And let's see. Let's start up here. So g prime of x is defined as the limit as h approaches 0 of g of x plus h minus g of x all over h. So we're just doing the general one here, right? Like we're not doing g prime at 4 or something, right? If we want g prime at 4, then when we're done, we can just stick a 4 in. Stick a 4 in it, it's done. Equals the limit as h approaches 0. So g of x plus h is going to be what? The square root of 2 times x plus h minus 1. Okay, minus g of x, which will be the square root of 2x minus 1, all over h. Now, how do we get the h out of there? We're going to have to rationalize the numerator, right? And in doing so, hope that a factor of h pops up, which can then be canceled. Okay, so we're going to multiply by, all right, so let's bracket things. I don't suppose the h does. All right, so what do we got? The square root of 2 times x plus h minus 1 plus the square root of 2x minus 1. Bracket, right? And what goes on the bottom? Same thing, right? And because this over this is just 1, right? So we're not changing its value, we are changing the form. So 2x plus h, oops, should be a bracket there, minus 1 plus the root of 2x minus 1. All right, so that's equal to the limit as h approaches 0. Okay, so the top is now set up as a difference of squares, right? Okay, so that's easy to multiply. It's just going to be, you square the first square root, so that's 2 times x plus h minus 1. Okay, and then we've got the plus and the minus, middle terms are gone. And then minus, so let's just throw brackets around that, minus 2x minus 1. All over h.
So you still need to have like the
And
on the bottom?
yes, you're right. H. Yeah, it couldn't have been that easy, right? Plus. Okay, there we go. All right, so what do we got up top here? So we got the limit as h approaches 0 of 2x plus 2h minus 2 minus 2x. Oh, sorry, minus 1. Where am I getting 2 from? Minus 1. I want to multiply everything by 2, not just these guys. Minus 1 minus 2x plus 1 over h times, and then 2x plus h minus 1, extend the square root sign, plus root 2x minus 1. Okay, so switching to red, the 2x and a minus 2x, and we got a minus 1 and a plus 1. Okay. And what else can we cross off? The h, right? Okay, because all that's left up here is a 2h. Okay, so the h's. Well, actually, now then we can lose the limit now, right? Because what have we got? So we've got 2 over square root of 2 times x plus 0 minus 1 plus the root of 2x minus 1. So 2 times x plus 0, that's just going to be 2x minus 1, and then we've got adding on another root 2x minus 1, so there are 2 of the root 2x minus 1s. So that's 2 over 2 times the root of 2x minus 1, and the 2's cancel. And we are left with g prime at x is equal to 1 over the square root of 2x minus 1. Okay? And neat. And then in the next few days, we'll get some rules where we can just go straight to that result without doing all of that.
Right, so we have to rationalize the non-integrator.
No, I would you just leave that. Okay. We're into rationalizing numerators now, right? So doing rationalized denominators. What are the domains of G and G prime? What was G? So G of x equals the root of 2x minus 1. G of x equals the root of 2x minus 1. Okay, so what's that domain? Yeah, so 2x minus 1 has to be greater than or equal to 0. So 2x has to be greater than or equal to 1, and x will be greater than or equal to 1/2. Okay, so what do we got? Set of all x such that x, okay, or, greater than or equal to 1/2, 1/2, comma, infinity. I way prefer the bracket notation.
The other one builds character.
Well, it's bracing.
You have to write more.
Yeah, should be an x belongs to the reals in there or something. So what's the domain of g prime of x?
It's the same thing, but because it's on the bottom, the root of 2x minus 1 can't be equal to 0.
Yeah, so it's the same thing, right? Except, yeah, we can't have a 0 here. You can have a 0 here, who cares? But you can't have a 0 here. So then g prime of x, which is 1 over the root of 2x minus 1, so the domain is x is strictly greater than 1/2. Set of all x such that x, or round bracket 1/2, comma, infinity. Okay, and then if we wanted any particular g, or the slope at any particular point on this, all we have to do is substitute in the x, right? And we can get the slope at any particular point. And then if we want the equation of the tangent line, once we've got the slope and we know the point, right? Let me just run through. Show that f of x is equal to the absolute value of x is not differentiable at x equals 0. Okay, so we want f prime of 0, right? We want to find, well, we're going to say, can we find f prime at 0, right? So f prime at 0 is going to be f of 0 plus h minus f of 0 over h. All right, so f of 0 plus h would be the absolute value of 0 plus h minus the absolute value of 0 over h.
Should that be a limit?
Right. Good catch. Limit as h approaches. So it's going to be the limit as h approaches 0 of what? Just the absolute value of h over h. Now, we know that the absolute value function kind of does things, right? Like around 0. So if we approach 0 from above, then what's the definition of absolute value of h? So if h is positive, then absolute value of h is simply equal to h, right? Do I want to show the absolute value here? I don't think we need to, right? So limit, well, yeah, sure, let's do it. So of this is equal to h over h is equal to 1, right? H over h is just 1. What if we approach h, or sorry, what if h approaches 0 from below? Then how do we define absolute value of h? So it would be negative h over h, right? Because the absolute value, if we know the value is negative, the absolute value is the negative of a negative to make it positive. So this is negative h, but then what's this equal to? That's negative 1. So since the two one-sided limits are not the same, okay, so since the limits are not the same, then f prime of 0 does not exist. Does not exist. And then is there something at the bottom? In general, functions whose graphs have corners or kinks are not differentiable there. If there's a sudden change in the direction of the graph at x equals a, then the function is not differentiable at x equals a. Okay, so you need a gradual change, a gentle. Think of a nice little cubic gently. Yeah.
What's the definition of differential or differentiable?
So if those two one-sided limits are the same.
Oh, okay, so it's just continuous.
Yeah, it's got to be continuous. Now, it can be continuous and not differentiable. This is continuous, but there are places where it's not differentiable.
Oh, okay.
So the graph of y equals f of x shown right. State the values of x where the function is not differentiable. So where's the first place? X equals -3, right? So you've got that sudden turn. You got a kink in the graph. Where's the next place where we are not differentiable? What?
I don't know. I'm very confused.
Okay, so we're moving along here. We said, all right, so that's a problem. Where's the next problem?
Can't you still get the limit there, though?
Wouldn't it exist because both sides are...
But they have different slopes, right? What is it? It's the instantaneous slopes, right? They have different slopes. One's positive, one's negative. Just think of the absolute value, right? It's got that V shape. That's a kink, right? Or a corner, right? It changes too suddenly. So the next place will be where? Down here, right? It's not continuous.
But can't you still read the limit there?
Yeah, but it's got to be continuous. That's part of the definition of differentiable. Must be
Okay.
continuous.
This is the instantaneous thing.
Yeah, it's instantaneous.
Oh, okay.
At that instant. Okay, where's the next problem?
3.
Okay, at 3, right? You got a corner there. Where's the next problem? Here. You got another problem. Where's the last problem? 6, right? Because it's only one-sided. Okay, so it's only a one-sided limit. And this guy here, right, this is a discontinuous, so discontinuous here. To be differentiable on an interval, you have to be differentiable everywhere on that interval. Right? That's continuous. Okay, now example 5 is kind of fun because what it's doing is we're going to look at a graph and we're going to graph the derivative, right? So which one's probably easiest? See, everybody says B, but it's A. So if you look at it, you say, well, what's the slope of this little segment here?
It's 6.
1, 2, 3, 4, 5, 6. Yeah, it's 6, right? Okay. So what's the derivative? Well, derivative is the slope of the line. This slope is constant, right? From here to here, here to here, it's 6. Right? Open circles, right? Not defined on the other side here, and there's kink there. What's the slope from here to here?
1.
Okay, so like 1, 2 over 2 is 1. Okay, so we're going to go down, and from here to here, the slope is 1. Okay, what's the derivative? Just the slope, right? What's the slope from here to here? 0. Okay, so from here to here, the slope is 0. What's the slope from here to here? So what do we got? 1, 2, 3, 4, 1, 2, so -2, right? Because now this is going down to the right, so we're going down 4 right 2. We have a slope of -2. That goes from here to here. Okay? Because each of these sections has a constant slope, right? They're just straight lines. So they have a constant slope. You know, what's the slope? Well, you just figure it out. And then from here to here, the slope is 1. Right. There we go, right? Easy peasy. Straight lines are easy, right? I mean, because they have a constant slope. These don't, right? But we can work out instantaneous slopes anywhere. Now we're just going to sketch the graph of the derivative. Right, so we don't actually have to work out the exact, you know, don't have to sit down here now. We're just sort of sketching the graph. So what I just want you to think about is, okay, so what's the slope along, what can you say about the slope going from here to here, or any of these slopes? You know, they're all going to be positive slopes, right? So slope here is positive, slope here is positive. Now what's happening to these positive slopes? Are they getting bigger or
Smaller.
they're getting smaller? And then at this point, what's the slope?
0.
So at this point, the slope is going to be 0, right? It's going to be coming across. So here, we know the slope is 0. And we know that to get from here to here, we've got some reasonably large positive numbers that are getting smaller, right? So we've got a slope that's coming down to 0, right? Positive numbers going down to 0. Now what can we say about these slopes?
They're getting more negative.
Yeah, they're negative, right? They start off pretty gradual negative. So from 0, right? They were positive, they hit 0. Now they're going negative. Yeah, it's slowly at first, and then very steeply getting negative. And so that's what the...
So would the graph kind of curve like it, like would it curve through the x-axis there, or is it just straight through?
Yeah, so okay, what do you think?
It would curve through, wouldn't it?
Well, would it? So what degree is this? This is degree 2. What does this look like? It's degree 1. Okay, now we're actually going to go look. So here is a Geogebra thing that some guy did. And what it's showing is the tangent, right, and the slope. So if I take point T and move it, if I can take point T and move it without drawing lines, come on. You're supposed to interact. No, damn it.
Maybe you think
You're moving something, the wrong thing.
Yeah, there. Oh, what, does this move? No. Okay, come on. There we go. All right, so I have to select this. Okay, so what's happening here? Well, so if I go up here, we're getting larger positive slopes, right? Okay, so let's take this and go up here, and you can see that the slopes are getting larger positive numbers. Okay, so if I come down here, well, we're getting smaller positive numbers. What's going to happen when we hit down here?
It's gonna hit 0.
It's going to hit 0, and then it's going to go negative. Okay, so here come the slopes. Here's the slope trend, and it hit 0, right there. So it hit 0. So this tangent line, and then we've got negative, and we got a straight line. Right? So now, switching views, we go to this one, which actually just shows the line, right? And this is actually showing, here is the function f of x, which is x squared over 6 minus 2x plus 8. And here's f prime of x, which is x over 3 minus 2. Right? And we say, oh, okay, this is a degree 2, the quadratic, but this is linear. X minus 2. And I can still move these, right, and it'll trace along, but now you can see the whole line. Okay? Kind of neat, huh?
Yes.
Okay, now let's go back to this. Okay, so that's what we've got there. Right? And then, of course, this is just going to do this. Now, what kind of graph this? This is a cubic, right? So what kind of slopes do we have coming along here? They're positive slopes, and then they're getting smaller until they reach 0, right? Because that's where it's going to turn. So at 0, which would be like about here, that'll be a 0. So now the slopes, so they were positive, they're 0. Now they've gone negative. Okay? So we got negative slopes, and then what happens to them here? So I mean, there's actually, there's a point here we can sort of figure out the slope, right? Because it's kind of almost straight. We know it's not, but it's straight-ish. So we got negative slopes, and then they do what? Well, that's a 0 there. So these negative slopes get larger, and then they're going to get smaller, right? So we're going to get kind of, some largest negative value till we get down to around here somewhere, where, I don't know, what's this slope? 1, 2, 3, 1. So about maybe -3 is kind of the slope along here. So we say, well, okay, get to about there, that slope. Then this is 0. So they get smaller negative values, so larger negative values, smaller negative values, till we get to 0 again. And then what happens? Then they go positive. And these guys were larger positive, right? And we end up with something along these lines, which can be demonstrated with this one. So this is a cubic, right? X cubed over 18 minus x squared over 4 plus 1. We got the same deal, right? So these are positive, so if I just go up here, right, we're just going to get larger positive numbers. As I come down, then the positive numbers get smaller until at this point they hit 0, right? Then what happens? Well, what kind of slopes are these? Negative, right? It's going down to the right. So I'm going from 0. I've got some small negative numbers, which then, so they're kind of small here, and then they get bigger, they're 0 here, be a little bit bigger, then they start to get smaller because right here the slope is going to be 0 again. Okay, so we got some small negative numbers, get big to a point somewhere around here, and then they get smaller until they hit 0 again. And then small positive numbers getting to be large positive numbers, right? As we go here. So guess what the next one is? So then here's this, but it's showing the traced out curve of the derivative, and it's giving you the equation, right? So the original function is cubic, but the derivative is quadratic. Right? Interesting thing, right? And we can see what's going on here. Again, and I could trace along, and you can see the values going to 0, Then some smaller negatives getting to be larger till about kind of halfway here, right? And then they start to get smaller again to 0, and then they go to positive and large values. Peter, I don't know how sensitive the microphone is, but it is recording.
I'm sorry, future people listening.
You know, what if there's some 7-year-old watching?
You're a genius. You're my hero, 7-year-old child.
Could be. You'd be talking to 7-year-old you. I could be watching this. No, there's no time travel. Other notations for derivatives. Okay, so nothing to write here. This is just right here, just showing you how. So in example 1, you found that if f of x was 2x squared minus 4x minus 1, then f prime of x was 4x minus 4. If the equation was expressed instead as y equals 2x squared minus 4x minus 1, then the derivative would be denoted by the symbol y prime. Okay, so if we have f of x, the derivative is f prime of x. If we have y equals, then the derivative is y prime. Okay, just notation. Another notation called Leibniz notation. Who discovered calculus, Newton or Leibniz?
Newton. Separately.
Yeah, separately. And who published first?
Leibniz.
Yeah, Leibniz had something down, yeah, and Newton had written something, but it was in a code, right? It's like, I've encoded this to be, and that. There's actually, you know, it's kind of interesting. There's some videos that are actually showing Newton's notebooks, right? Usually, you know, May 4th, 1620 or something.
So Leibniz was a bit derivative.
Yeah. Well, so, and he's got his own notation. So if y equals f of x, then in Leibniz notation we go dy by dx, right? Kind of think of that as like delta y over delta x, right? Like a change in y over the change in x is f prime of x. So in example 1, you found that if y is the root of 2x minus 1, then y prime is 1 over the root of 2x minus 1. We can also say that if y is root 2x minus 1, then dy by dx. Okay, so you got f prime of x if it's f of x, you got y prime if it's y, and you've got dy by dx if we're using Leibniz notation. Another way you can say this is to make this look like an operator, right? Like it's saying d by dx of, right? And all we're doing is, because that's y, right? Y was the root of 2x minus 1. So we're saying we'll do d by dx as if it's a differentiation operator. Take the derivative of, right, is equal to. And if you want to evaluate a particular derivative of x equals a, then we can write dy by dx and put a bar down and say x equals a, right? Put a vertical line and say you're going to evaluate that. So that's the derivative evaluated at x equals a. Leibniz notation is good for emphasizing the derivative is the instantaneous rate of change of y with respect to x, right? So it implies change of y with respect to a change in x, right? Or the change of y with respect to x. A third notation for derivative, you're not going to see this that much, but it's d f of x is equal to d sub x y. Following notations can be used for derivatives. So y equals f of x, f prime of x, you're going to see that a lot. Y prime, you're going to see that a lot. dy by dx, you're going to see that a lot. d by dx of f of x, you're going to see that a lot. Not going to see this so much. Okay, but yeah, I mean, if you're looking at another book or you're looking online, then they may be using different notation. You just recognize it. Oh yeah, they're all just different ways of getting across the same thing, right? The derivative. All right, that's that.